So next up is ozonolysis, a very specific and different type of reaction in our addition to alkenes. Now, ozonolysis is going to occur in multiple steps via a 5-membered ring intermediate. Now, we're not going to need to worry too much about what this intermediate looks like or its mechanism, but we are going to need to know about the products of this reaction. Now, an ozonolysis is a really useful reaction because it serves to cleave the carbon-carbon double bonds to make new carbon-oxygen double bonds, aldehydes, ketones, and acids specifically. A di-substituted alkene will always generate a ketone product, but a monosubstituted alkene has some choice, and that's where different workup steps will come in. A monosubstituted alkene will make either an aldehyde or an acid, and this will depend on the workup. A reductant can also be used in this reaction in the workup step to make an alcohol, as we'll see. So let's take a look at these different types of reactions. We start by looking at a mono and di-substituted alkene, depending on which end you're looking at. For carbon 1 up here, you'll notice that there's a hydrogen atom that is implied but not shown. Carbon number 2 down here is di-substituted. Now, the first step of all of these reactions is going to be the addition of ozone, O3, up here. Now, the addition of ozone is then followed by a series of workups. We're going to start with this workup here, dimethyl sulfide. You may see this abbreviated as Me2S. Now, Me2S is considered a mild workup, which is going to be important when we think about the resultant product. Now, carbon number 1, which I highlighted in pink, is here. And you're going to notice importantly that this here gives me an aldehyde because I used a mild workup step. Now you'll notice carbon 2 is a ketone because di-substituted carbons always give ketones regardless of the workup. So ozone followed by this mild dimethyl sulfide workup give di-substituted alkenes as ketones, always, and monosubstituted alkenes as aldehydes. Now let's look at a more aggressive workup. Here we have, again, ozone first, followed by hydrogen peroxide. Now this is a stronger workup. So let's see the consequence of what happens here. Now carbon 2 in green is carbon 2 in green. Di-substituted goes to ketone. So the workup doesn't matter there, but the workup matters a lot with this monosubstituted carbon up here. This gives the carboxylic acid. And the reason why it gives the acid is because of this strong workup step. Now, I said earlier that we can also use sodium borohydride here. This is a reducing agent, which you'll see more of in other sections, but a reducing agent will both cleave the bond after that ozonolysis and give a reduction of the carbonyls to give us the alcohols here and here. So, ozone used as the first reagent in all of these reactions, followed by 3 different types of workups. Dimethyl sulfide is mild and will give the aldehyde from a monosubstituted alkene. Hydrogen peroxide is a stronger workup, which gives the acid from the monosubstituted alkene. And sodium borohydride can be used to give an alcohol instead of that carbonyl. Now what we're going to do is we're going to predict the product of each of these reactions. Before that, just keep in mind that I have summarized for you the 3 different workups. So the mechanism for this reaction is pretty complicated and you don't need to know it, but what you need to know how to do is draw the products of those reactions. Now, one of the most popular types of question in this chemistry is to give you alkenes that are contained within a ring. The reason for that is you have to be really careful about counting your carbons. So I'm going to walk you through how I think about these questions. So we're asked to predict the ozonolysis product of this first reaction. We know that ozonolysis cleaves the double bond. So I like to scribble through the middle so that I can keep track of things. And then what I like to do is I like to number my carbons like so, just to keep track of all of them. And I'm going to try and maintain a little bit of that ring structure in my final product here as I think about it. Now I have to keep in mind of the two types of carbons that are present. Carbon 6 here in yellow is di-substituted, and carbon number 1 up here in green is mono-substituted, which means I need to think about the products at the end of the reaction pathway. Now I take a look at my workup. The workup here is dimethyl sulfide, and since I'm using dimethyl sulfide, that is a weak workup step, which means I should get the aldehyde. With all that being said, I'm going to get an aldehyde here and a ketone here. And just for good measure, let's count those carbons. 1, 2, 3, 4, 5, and 6. Perfect. So just a quick tip to just sort of help you out with keeping track of all those carbons. Let's see if we can do the same with this reaction below. Now this one's especially tricky because yes, it's contained within a ring, but there are also two alkenes that we're going to split here and here. And you'll notice again that we have dimethyl sulfide as the workup. So it's almost as if we're going to be cutting this ring in half and have two separate pieces. So let's number the carbons on both sides. 1, 2, 3. Up here, and on the bottom 1, 2, 3, 4, and 5. So I'm going to draw the 3 carbon piece here, 1, 2, 3, and I'm going to put in that group that it has. You'll notice that I have not touched the stereochemistry. No chemistry has happened there, and therefore I should not affect its structure or stereochem. I'm going to do the same with this green bit here. So down here, 1, 2, 3, 5, and I'm going to put this group in again, and you'll notice again that I haven't affected the stereochemistry where no chemistry has occurred. And just for good measure, I'm going to number these carbons because I want to keep track of things. 1, 2, and 3, and down here, 1, 2, 3, 4, and 5. So the last thing to do is look at the workup step. It's at dimethyl sulfide, so I should have aldehydes where I have mono-substituted alkenes. So we'll go back in, we'll take a look. This is mono-substituted, this is mono-substituted, so is this one, so is this one. I should make a whole lot of aldehydes, so let's do so. Carbon number 1 here should have an aldehyde on it, like so. And carbon number 3 should also have an aldehyde, like so. Carbon number 1 down here should have an aldehyde, like so. Carbon number 5 should have an aldehyde, like so. And I am done. An especially tricky reaction showing that we need to cut this whole thing in half. So ozonolysis, you are not responsible for the mechanism at this level, but you are responsible for predicting the products. Remember, use that sort of cutting motion through the center of the alkene like I've done here. Keep track of your carbons as that's a really common mistake, and then look to the workup. Is it mild, like dimethyl sulfide, to give the aldehyde, or is it a stronger workup to give the carboxylic acid? Watch out for sodium borohydride, which would give the reduction to the alcohol.